Hello and welcome to University of Physics 1 online. Today, in our very first lecture, we're going to discuss what physics is. We'll form a little bit of a historical background for it, and then we'll start talking about units and standards, which will be the first big topic of the course. Now, this is the first lecture of 2 out of chapter 1 in your book. And don't forget, you can find the book under the contents section of your course. It's free. Now, that said, let's start with the definition of physics. Now, if you've had physics before, or maybe you, out of interest, looked it up in the definition in a dictionary, you may have come across something that looks a little bit like this. So, let's see here. So, physics is the study of matter, energy, and how they interact. Now, this is the modern definition of it. As we go through the history part of today's lecture, you'll see that that's not always been the case. Now, what do we mean by the study of matter, energy, and how they interact? Well, thanks to the work of Albert Einstein, we know that matter and energy are equivalent but not the same. And it turns out that the way the universe works requires that we look at how matter interacts with matter, how energy can interact with energy, and how matter and energy can interact with each other. A good example of that would be reflecting light off of a mirror. Light you can think of as being energy. A mirror, however, is made out of matter. So obviously there's some sort of interaction between energy and matter at the interface where light hits the mirror that causes it to reflect and follow the law of reflection. Now, that said, let's take a look at sort of the historical way that physics started. Now, to understand that, we need to talk just a little bit about this guy right here. Let me resize this so it's not so crazy. So this guy right here, his name's Aristotle. So this is Aristotle. Now, he is an ancient Greek philosopher. Greece. Incidentally, Greece is where the study of philosophy began. And from a chronological standpoint, he was alive roughly around 380 BCE. All right. Now, as you might not be all that surprised to discover, we didn't know a whole lot about nature back then. That's part of what philosophy was created for, was to give us a foundation to study these sorts of things. And Aristotle, among other things, tried to understand why it was that things moved. Now, in Greek physics, just write this out here. In Greek physics, things were a little bit different than how they are today. So their view held that an object's natural state with respect to motion at least was at rest. Now, you may already know, or if you don't, you will discover that that's not true. There is no natural state to be at rest. An object that's moving will continue to move. An object that is at rest will continue to stay at rest. unless acted upon by some sort of external force. That's one of Newton's laws. We'll talk about him momentarily. Now, so basically, this belief that was sort of fostered by the ancient Greek meant that if something was moving, there had to be a reason for the motion. And Aristotle's answer to that was to look at the idea of elements. Now here, when we say elements, we almost mean the chemistry definition of element, but it's very crude. It's almost like a proto-idea, a proto-element, if you will. In Greek philosophy, they believe that everything in nature was made of things like, say, fire. You could have water in something. You could have air in something. And you guessed it, you can have earth in something. Now, so everything in nature was comprised of some combination of fire, water, air, and earth. And as per Aristotle's idea of physics, things moved based upon their composition. So, for example, let's see here. Let me page on to here. So, see, you can draw a circle here. It's a big experiment. This is a new app. So, this right here, we're going to call Earth. So this is Earth. Whoop. Well, that's interesting. Not what I was looking for. Do I have to turn it off? Yeah. Okay. So, this would be the element of Earth. Now, sitting above Earth, it's a four circle, but we'll deal with it. You have water. Now, does this make sense? Well, okay. If you were to go to the ocean and look out, you would see water, but if you swam to the bottom of the ocean, what would you find? You would find Earth. Now, next, sitting above that, you have air. And sitting above that, you have fire. Now, all of this sphere of elements, if you will, is embedded in something called the ether. So, according to Aristotle, the reason why things move was because they were trying to return to whatever their natural state was here. So, for example, let's pretend that you take a piece of chalk. So here's a piece of chalk sitting in the air, and you let it go. It's going to fall down towards the ground. Now, why does it do that? Well, according to our modern understanding of physics, gravity. That's the reason why. However, here, they didn't have a concept of gravity. It didn't exist as an idea yet. So the reason why is because air, as you can see, sits above Earth. And if you look at chalk, chalk has many of the characteristics of Earth. It's dry, crumbly, etc., and so on. So it's falling to rejoin the Earth. That's the reason you see that motion. Now, if you were swimming underwater and you blew bubbles out of your mouth, the bubbles would rise. Why do they rise? Well, we know from a modern standpoint it has to do with the differences in density between water and air and basically fluid mechanics. Well, according to Aristotle, the reason why the air would go up is because air sits above water, so it's trying to rejoin the air that sits above it. Now, at the interface on a cold day, say between water and air, you might find ice. Well, if you look at ice, ice clearly has characteristics of Earth. It's hard. It also has, if you were to look at most ice that forms on a lake or something like that, air in it. So there's a balance between the air causing it to want to rejoin the air above and the earth causing it want to go down, and as a consequence you have it sitting on the top of water. Now, this is wrong. It's a nice attempt, but not quite what we're looking for. So, what's a better view? Well, a better view would be the view that was given to us by this guy right here. Now, this is Isaac Newton. Chronologically, he lived somewhere late 1600s. He did work from then until the 1700s. So what did he do? All right. Well, between Aristotle and a little bit before Isaac Newton, you had this guy named Galileo. He lived roughly mid-1600s. And Galileo typically is considered to be the first real empirical scientist. So he's the first empirical scientist. Now, what's that mean? Well, an empiricist is all about measuring nature. We say that the sciences are broken up into two rough areas. You have theory and you have empiricism. That's not entirely true. In truth, everything is a combination of theory and measurement. But long story short, Galileo, unlike scientists that had lived before him, believed that you couldn't just assume things about nature, that you had to measure stuff. And that you may discover through measurement that your beliefs were entirely wrong. And so what he did was to look at the physics that they had at the time, and this is before Newton, which was based on Aristotle's work. And by the time he was done giving it a good look, there was nothing left. Basically, the only thing that was left by the time Galileo was done was the concept of speed. He had added in the idea of acceleration. He had demolished the idea that an object's natural state was to be at rest, which, if you remember earlier when we were talking about Aristotle, that was one of the foundations for their belief. The way he was able to sort of demolish it was just by performing simple experiments. One of the things he believed was, and this is a revolutionary idea, one of the things he believed was that math was a good way to model nature, but it didn't give you a perfect description of nature. He believed that there were these things that were called frictions that you would never entirely be able to take into account, and that would cause your mathematics and your attempt at modeling nature and nature itself to always disagree a little bit. Prior to him, the idea of friction didn't exist. So imagine taking a tennis ball and rolling it down the street. Now, eventually, that tennis ball is going to come to rest. From a modern standpoint, it comes to rest because of friction. Eventually, its energy motion is taken away. So you take the energy away, it's not moving anymore, and that's it. It stops. Now, Aristotle's idea would be that the reason why that tennis ball comes to rest is because there's nothing making it move anymore. So, completely different way of thinking about stuff. He also coined the idea of inertia. Now, all of these concepts, speed, acceleration, friction, and inertia, we're going to come back and talk about later on. But with the exception of speed, all three of these things were new ideas. Now, so by the time Galileo was done with physics, and incidentally, he does the same thing with astronomy. He just annihilates it. Um, these are really the only concepts that are left, and everything else has been disproved to be wrong. So Isaac Newton comes along, and he takes the work of Galileo and spends a lot of time working on it. He actually ends up having to do it in seclusion because there was an outbreak of the Black Plague. He was in hiding trying to avoid people and not get it. And so what he does is he comes up with a type of mathematics that is needed in order to correctly talk about nature. Because the mathematics at the time was not well suited at all to talk about rates. Now, if you've had pre-calculus or you've already had calculus 1, you know that rate equations are equations that have derivatives in them. And derivatives tell us how one thing changes with respect to something else. That's a rate. So, how things change. With respect to each other. There is no foundation in mathematics at the time to correctly describe that. So he invents one. It's called the calculus of variations. Now, the calculus of variations, the important part being the variation part, allowed him to ask mathematical questions about nature. He also came up with 3 laws of motion. Okay. Now, because Galileo had done what he had done to astronomy, and now the entirety of astronomy was just one big open question, one of the things Galileo did was to look at the motions of the planets around the sun, and look at the motions of the moons around planets. He took his calculus, he took his 3 laws of motion, and he deduced the existence of gravity, and came up with a law for it. Now, the calculus of variations we just call the calculus today. However, that's kind of a misnomer. Calculus just means a calculating framework. That's the variations thing, like I said before. That's the important part. Nonetheless, these 3 things right here revolutionized science and actually formed the foundation for the physics that you'll be learning today, and also through the course of the semester. So, this allowed us to do physics, and as a consequence, allowed us to do astronomy, and eventually things became what they are today. But Newton's laws of motion, his calculus, and his law of gravity are not enough from a modern standpoint. So that said, let's talk about what physics today looks like. Now, so here's the deal. Newton's physics still works, but not everywhere. And that's because when Newton was doing his thing back in the 1600s and the 1700s, he didn't know about things like atoms. He didn't know about things like molecules. He didn't understand the concept of temperature. These sorts of things were expanded on after his work. So today, if you were to look at what is sort of contained under the umbrella of physics, you have approximately these things. You have what's called classical mechanics. Now, classical mechanics is really Newton's physics. Now, Newton did do some work with light, but his work with light was all done under the guise of classical physics. Subsequently, we discovered that that's not how light works. So, in order to talk about light, we have to talk about something called electricity and magnetism. Now, believe it or not, electricity and magnetism were both things that were also studied by the Greek. Electricity, for example, derives from this gemstone called electrum. Electrum today is known as amber. And it turns out that if you take a piece of amber and you polish it with wool, that bits of the wool will stick to it. It'll attract pieces of paper. So we know from a modern standpoint that that's due to static electricity. But to the Greek back in the day, that was a new phenomenon. So the study of electrum and its properties is called electricity. Likewise, magnetism is sort of a similar phenomenon. There's this place called, or at least there was this place called Magnesia. If you look at where modern day Turkey is, that's roughly around where Magnesia was. Now, they found these stones that would attract bits of types of metal, like, for example, iron. And so now you have a new phenomenon to look at, and the study of these stones from Magnesia and their effects, well, that's called magnetism. Now, it turns out that electricity and magnetism really are two sides of the same coin. That's something that we'll talk about in the second semester of this course. That said, when you put these two together, their behavior isn't like classical physics or classical mechanics, Newton's version. So, we had to expand on it. Now, you also have things like thermodynamics. And I'm going to put in parentheses here statistical mechanics. Now, thermodynamics is the study of heat, how it flows, and temperature. Statistical mechanics a lot of times falls up under the umbrella of thermodynamics too, because it describes how large numbers of particles interact with each other. I'm not talking about how 1, 2, 3, or 4 particles I'm talking about how Avogadro's numbers of particles interact with each other. Now, these are new ideas. So because Newton didn't know about this sort of stuff, we had to expand on his physics. Likewise, you have things like relativity. Relativity is what happens when you have things moving incredibly fast, a substantial percentage of the speed of light, or things are incredibly massive. So their behavior and how they can affect other things doesn't unfortunately fall up under classical physics. You have to expand on it. And lastly, but certainly not least, you have quantum mechanics. Now, quantum mechanics is what happens when you take a look at the behavior of atoms and molecules and things that are even smaller than that. The physics that happens there looks a little bit like classical mechanics, but it doesn't. So you have to expand on the old way of thinking. And as a consequence, all of these things, classical mechanics, electricity and magnetism, thermodynamics, statistical mechanics, relativity, and quantum mechanics, these all form what we think of as physics now. Now, that said, this is University Physics 1. University Physics 1, almost in entirety, deals with Newton's physics. Because even though Newton's physics is old, and even though it doesn't describe all of nature perfectly, it does describe a substantial percentage of nature, and it works well. And the ideas, the foundation that you get talking about Newton's physics allows you to talk about things like electricity and magnetism. It allows you to talk about things like thermodynamics and relativity and quantum mechanics. So without a good foundation in the old way of thinking, the classical mechanics, you can't do any of the other stuff. As a consequence, these things right here are typically University 2. And this is University Physics 1. Now, so let's keep on. So now that we've gotten the historical aspect of the course out of the way, what I'd like to talk about now is the role of numbers in physics. So as I had said earlier, a lot of times people think of the sciences as sort of existing in two distinctly different categories. You have theoretical sciences and you have empirical sciences. Like I said, that's not entirely true. So the idea is this. Theory is in the head. Those are ideas. Nature is reality. So the idea, or at least the goal here, is to somehow test our theory by doing experiments on nature. Okay? Now, when you do an experiment on nature, when you do some sort of empiricism, in order to measure nature, unfortunately, you have to deal with mathematics. I say unfortunately, I actually enjoy math. So, math is the interface, basically, between theory and reality, if you want to think of it like that. That said, what I'd like to talk about now, at least to begin with, falls up under the guise of something called units and standards. Okay. And basically, units exist to tell us basically what a number is in reference to. For example, let's pretend that I have a room. So here's a room. Let's draw one right here real quick. That's not a bad room, especially with a stylus. It's pretty hard to draw on these things. So we'll call this length, and this is width. Now let's pretend that you told one of your friends to go measure this room, and he tells you that the length of the room is 3, and the width of the room is maybe 1.5. Now, that doesn't do me any good at all. And the reason why it doesn't do me any good at all is the first thing you should ask yourself when you hear 3 and 1.5 is 3 what? Feet, meters, yards? How did you measure the room? Now, it's those things. Feet, or meters, or yards. It's these things right here that tell us the relevance of that number right there. Okay? Now, these things are called units. These are units. So, units tell us why the number is relevant to us. Okay? So, for example, a dimensions of a room that's 3 by 1.5 doesn't make sense. But if I told you that it was 3 yards by 1.5 yards, okay, now we're getting somewhere. Now we can talk about, what that measurement means. Okay? So that said, in the sciences, there are two basic systems of units. You have something called the imperial system. And you have something called, and this is in French, the international system. Now, the imperial system is what we use here in the United States. Okay, when we measure things here in the U.S., we measure things in feet or inches. Uh, inches. Maybe we measure temperatures in Fahrenheit. We measure, how much things weigh in pounds. We measure the mass of something in pounds mass, maybe in slugs. So these types of things right here fall up under the guise of the imperial system when it comes to units. Now, in the international system, you have things like meters, centimeters. Maybe we measure temperatures in Celsius. Maybe we measure it in Kelvin. We weigh things in newtons. We take the mass of things in kilograms or grams. Okay. Now, that said, System International, which is also abbreviated as the SI system or the metric system, is the preferred system of units that you see used. We're going to talk about why that is here in a moment. Suffice to say that you might have two systems of units, but you have three basic types of units. Now, the first type of unit that you see is called a fundamental unit. Now, fundamental units refer to things that you can measure in nature that represent some underlying property of nature, some base property of nature. For example, length. The distance between 2 points in space is a fundamental property of space-time. You can't break length down into other stuff. Length is length. Time. As best as we can tell, time is something that is not made of other stuff. It exists. It represents some sort of forward motion through, nature. Increase in entropy. That's one definition of it. But it is something that is not made out of other things. Mass. Now, the chemistry definition of mass is how much matter occupies something. You can use that definition in physics, although later on we're going to talk about an alternate definition of mass that centers around the concept of inertia. That said, the amount of matter present in something is a property of nature. Here's another example of one. Charge. Charge, it turns out, is also a fundamental property of nature. So length, time, mass, charge, these all represent some underlying property of nature that you can directly measure. Now, that said, you don't want to confuse these things with the idea of base units. Now, a base unit and a fundamental unit, you can have the same thing. They could be the same. But even though some fundamental units can be base units, that doesn't mean that all fundamental units represent a base unit. Now, that said, base units exist because when you look at an equation in physics or in chemistry or wherever, you need to make the decision as to what kind of units you're going to put in. For example, are you going to use kilograms? Are you going to use grams? Are you going to use newtons? Are you going to use Celsius or Kelvin? So base units are the units that we use when we actually plug stuff into an equation. They may not be fundamental, like I said, or they may, but they are the unit that you use when you're using an equation itself. So base units are the units that go into an equation. Now, the third type of unit that you see is something called the derived unit. They're not base units necessarily, although some are. They're not fundamental units at all. I'll give you an example of a derived unit. Units of speed or velocity. Okay? So speed, conceptually, is distance over time. Okay? Now, distance is a length. So from a unit standpoint, if you were working, we'll say, in the SI system, meters per second, or meters per second like this, would be the units of speed. But speed isn't something that's a base quantity. Now length is, time is, but speed itself is not. But it's made out of other units. Okay, and as such, it's a derived unit. Now another example of something that's a derived unit but is also a base unit would be the unit of force. Okay, so as per one of the ways that Newton wrote his first or second law, rather, F is equal to ma. Mass is kilograms, because a gram is very small. A is acceleration, and it is measured in meters per second squared. Now, this obviously is a derived unit. It's a unit that's made out of other units. But altogether, this big chunk of units is also called the Newton, abbreviated N, and it is a base unit. If you saw an equation that required that you put force in there, you would express your force in newtons and you would put it in. All right. So now that we've talked about the different types of units and the two basic systems that you see, what I want to talk about now are standards of measurements. Standards. Now, we're not going to spend a whole lot of time talking about this. It's just good to know. Because it turns out that standards are a good reason why we use the international system and why we don't use the imperial system. So let me give you an example. Let's talk about length in the imperial system. The most common things that we measure when we talk about length, or at least that we express in terms of units, would be inches, feet, miles, stuff like that. Now, an inch literally is defined as, if you look at your pointer finger, it's the distance from the tip of your pointer finger to the first knuckle. Now, I think we can all agree that different people have different sized hands. Uh, so what that means is that if you have 10 people in a room, and they use that definition, that standard, we'll say, for an inch, and they measure something with it, that you're going to get 10 different answers. Likewise, the foot was originally defined as the length of the king's foot. Well, which king are we talking about? If you change kings, now you're changing the definition of your foot. And if you were to have people measure the dimensions of a room using their own feet, you're going to get different answers. Now, so that's one issue that you have with respect to standards. Now, these days, from a modern standpoint, inches, feet, and miles are all incredibly well defined. They're defined off of physical quantities. But back then they weren't. And that's a problem. They do not have good standards. Now, not only that, if you want to go from a foot to inches, we know that there are 12 inches in 1 foot. What if you wanted to go between feet and miles? Well, there's 5,280 feet in 1 mile. Already my head is hurting because there's no clear relationship between 12 and 5,280. So in order to be proficient in the imperial system, going just between the units themselves and looking at their standards can be problematic. Now, if you look at the metric system, so we'll look at length. And, metric system. You have centimeters, meters, and kilometers. These are all equivalent here to this. They're not obviously the same lengths, but they're analogous to each other. So what does this mean? Well, okay, you have 100 centimeters in 1 meter. You have 1,000 meters in 1 kilometer. Look, powers of 10. Super easy. Now, the nice thing about this is the prefix on these things. Kilo, centa. This is, by the way, is the base unit. Also in the imperial system, this is the base unit. So what this means here is that in order to get from centimeters or kilometers into meters, all I need to know is something down to a power of 10. So if I were to, for example, go here and put an image here. So if you take a look here, for example, centa. So here's base unit. This would be where your base is. This is your base unit right here. Whether it's the base unit of length, base unit of time, whatever. Well, actually time is not correct, but the base unit of length, base unit of mass, what have you. So so here, let's pretend that I told you that something was measured in megameters. Well, 1 megameter see a 10 to the 6 is 10 to the 6 meters. And that's the relationship between them. So here, with the imperial system, in order to know the relationship between the different units that measure a particular quantity, like for example length, you need to remember all these weird conversions, Let's go down right here. So you have all these complicated conversions here, right? But in the imperial system, the metric system, it's just powers of 10. And that's something that you can very easily look up. And that's one of the reasons why in the sciences we prefer the metric system and not the imperial system. So, this is a good place to stop for our first lecture. In our next lecture, we're going to talk about how you convert between units. And also, we're going to talk a little bit about dimensional analysis, which is a very good tool to use.